Good afternoon to all of you. I am Rafat Jahan, student of MSc final year. It gives me immense pleasure to extend to you to a very warm welcome on behalf of the Department of Physics of Government MH College of Home Science and Science for Women, who has clubbed all of us for the illuminating webinar on exhaust and fueling technology development for a fusion reactor. It's my great pleasure to introduce the Promethean and ingenious speaker, Dr. Ranjana Gangradey ma'am. Currently, she is the Scientific Officer G in Institute for Plasma Research, IPR, Gandhinagar, Gujrat. She has completed her graduation from Government Autonomous Science College, Jabalpur, Masters of Science from Rani Durgavati Vishwavidyalaya, Masters of Philosophy from the same university. She is a member of Indian Cryogenic Council ICC, Indian Vacuum Society IVS, Plasma Science Society of India PSSI, and also a member of Vacuum Review Board of an international forum for LEGO project. She developed the technology of cryoadsorption cryopump using coconut shell charcoal technology. The technology is successful and three pumps of 400 opening are developed for Space Application Center, which is one of the major center of Indian Space Research Organization ISRO. This cryopump is patented as novel cryogenic vacuum producing system. Also, 50 students in the same research field are under her supervision. I request the respected teachers and my fellow companions to keep their mics and cameras off during the session. And if you have any questions or query to the speaker ma'am, you can drop your name in the chat box of the meeting. Now, I would like to invite and hand over to our Honorable Correspondent Ma'am, Dr. Ranjana Gangradey.
Thank you. Thank you for the introduction. Hello. Hello. Hello, everybody. I hope I am audible. And now we go ahead with our talk. Before this, as I have been introduced, I am an alumni of the Jabalpur University. And in fact, I am a complete, what do we say in Jabalpur, Jabalpuria. So I was, in fact, I was born in Jabalpur, in this Elgin Hospital near railway station. And was educated at St. Joseph. Hello, some disturbance is coming. Anyway, so I was educated in up till 8th class in St. Joseph Higher Secondary School, Jabalpur. And then I went to the St. Gabriel School, Ranchi. The schooling was at Ranchi near Engineering College. And then I had done my bachelor's at Science College, Jabalpur. And the MSc and MPhil at RDV, the university. So it's my pleasure to really give this talk. It's not very technical talk. It is a motivational talk showing you, yes, there are so many fields wherein the young generation can venture out depending on their liking and capability. Also, there is a small thing I would like to say, that how destiny plays a role. You know, when I from my KG class to my MSc, there was no electricity in my house. So I went ahead with all the studies with a lamp, studying in the lamp, that kerosene lamp, I still remember it. And then it was only in the MPhil when I came that we had electrical power in our house. So after the day the electrical power came, I could feel that what it is to sit in the fan and enjoy the breeze, instead of going for the silbata, we had mixer, etc. And that also you don't have to draw the water from the well using all ropes with all the, the wounds coming on the hand. You can use a motor and just take water from the well. So the role of electricity in the ease of our going ahead with the ease in our life, I realized then. And looking at that, my destiny has put me into a place where for the future generations to come, I'm contributing minuscule though, but yes, a future source where our generation 100 years from now can have electricity, because right now even we are short of, and slowly as we are advancing, we will still need more electrical power. So I am thankful to Dr. Shobha Johri for inviting me to give this talk, and also during the era when 75 years of independence has been completed, and it's a high time that the young generation should come up developing the technologies in the country. We cannot depend upon foreign countries for import of all the equipments and items we require for our research or going ahead with the high-end technologies. So we all look forward to you all for developing new technologies and making our country self-sufficient. Importing hurts, because a lot of foreign exchange goes as import to the developed countries. And we look forward to the young generation that they come up and develop the technologies for the country. So as I said, destiny has put me in a place where we have to look forward some new method to produce electricity. So presently I am working as a group head at Institute for Plasma Research. This is this is the institute under Department of Atomic Energy. And the main focus of this institute is to work on fusion research, fusion plasma research, and also develop on the side technologies which can help the industry with plasma applications. So this was my introduction. I am one of you. 35 years down the lane, I was like you all, sitting, roaming in the corridors of Home Science College, and looking forward to what can I do in future. Also, I was not that lucky to have so much of exposure as you all have. You all are born in an era where you can connect to the world in just a touch of the finger. So utilize this opportunity which you have got to really do something which can benefit our country. So with this note, I'll just give a glimpse of what we do here at the Institute for Plasma Research. And I am trying that to simplify the things. so that you all can understand it better, and rest you can do the Google search. So, coming to the energy requirement. The energy requirement is a growing problem. You see that the fossil fuels will last for 53 years around. The coal may last for about 110 years. So nuclear fuels, uranium, etc., may last for 80 years or so. So we will, as we go ahead in 2100, probably we'll be having very less electrical, our requirement will grow. So there is a poem saying that, not a poem, a saying that my grandfather rode a camel, my father rode a camel, I drive a Mercedes, my son drives a Land Rover, his son will drive a Land Rover. But what about his son? So his son will ride a camel if we are not boosting up to develop a source for producing electricity which can cater to the requirement of the growing world. So you can see how much power we use. 1 terawatt is 5 billion barrels, and in a year we use about 23,000 terawatt. So, and you may be looking forward to renewable energy resources, but these are only 19% of the total requirement what world wants. So if you see this graph, right now we are here at 2000, by 2100, what will happen? We will have, our energy requirement will be more, and what we will be producing will be less. So the shortfall will keep increasing. That is why they say that in the fourth generation, my grandparents rode a camel, so my fourth generation will again ride a camel. So we don't want that our coming up generation should live in dark and ride a camel. So we have to do something. So who has to do? You all have to do. You all have to come up finding out the technological solutions to go ahead. So here is another graph showing that how, as we improve our living, with more luxuries, with the initially we were good with the fan, then we came up with mixer, with the air condition at house, with the electrical vehicle, etc. So as the state of living increases, the requirement for electricity increases. So we will have to address this for our coming generations. Now, what is the state of India? India's energy resources. We have all the energy, most of it coming from coal. From hydroelectric power, it is about 13%. And other renewable sources like wind, solar, bio, it is only about 20%. So where do we go from here? What should we do? What is the answer to it? Nuclear fusion. Now, nuclear fusion. What is nuclear fusion? If I were there giving you a live talk, I would have asked you in an interactive mode. But on this online lecture, you may think at your seat that what is nuclear fusion? Where do you see? Every day you are seeing actually a nuclear reactor, fusion reactor coming up in the sky, giving you light and heat the whole day, and then setting in the evening. So what is it? It is our sun. Our sun and fusion. So what is happening in the fusion? I mean, due to you all are all from physics, I need not say much on it because my time limit is small. So our sun, just like any other star, it is a nuclear fusion reactor and is burning since 3 billion years and will continue for another 3 billion years. So can you imagine how much the sun produces? It's about 10 to the power 26 watts every second. And it is much, much more than what our earth consumes per hour. So if we can, make a sun on earth, probably we can solve the electrical problem of of the mankind. So when you sleep in the summer season on a cot in the night, looking at the stars, those are blinking. Have you ever imagined that these are all fusion reactors, big fusion reactors, twinkling light years away from us, and how nature is managing them very well, and to feel the extent how much energy a fusion reactor can give on a summer day, June or May. Just stand on the sunshine at about 2 o'clock or 3 o'clock and feel that how much heat you feel, and the radiation. So you have to wear a black goggle and just to have a feel that so many thousands of kilometers away, this fusion reactor is sending the heat waves, piercing our skin on another planet Earth where we are. So if we can make a fusion reactor here, our problems will be solved, right? So going ahead, what does our sun do? It's a super giant star. It has continuously, there is a fusion reaction going on there, and at its periphery there is hydrogen fusion, helium fusion. Then as you go inside, there is a iron core at the center. So what we have to do then, how does sun do? It is producing such a huge amount of heat, light, energy. It's all because of fusion. And what is fusion is, you all know that light nuclei joining together to produce a bigger one, and the remaining mass, which is the mass defect, appearing as energy. So the pressure generated in the sun due to the gases and the heat gets balanced by its gravitational pull, because it's very massive. So here the way the fusion is taking, the way the energy is getting released is due to fusion and the Einstein's delta mc square relation, which you all know. So what should we do? Sun, what happens is there is a confinement of the now just let me devote a few sentences to what is plasma. So plasma is the fourth state of matter. We have solid we heat, it becomes liquid we heat, it becomes gas we heat, it becomes ions. So a mixture of electrons and ions is called plasma. So it's a very vast subject with the theory on it and the application of it in the industrial field to whatnot. So this plasma is confined in the sun by using gravitational pull, whereas what we have to do here and how we will confine here, we will see in my other slides, coming up slides. So, in the sun, as I said, the confinement of plasma and the fusion, for fusion reaction to happen, you have to go to the fourth state of matter, that is plasma. In order to have a fusion, you had to confine the plasma and make these ions to move with a very high speed so that they collide and produce fusion. So the concept as how to confine this plasma was first given by Russians. The word is tokamak, which stands for toroidal chamber with magnetic coils. So what is done in this? In this, you have all read about solenoid, straight solenoid. So if you wound a wire around a straight solenoid, you get how much the magnetic field inside it is mu 0 Ni, right? All must have read this in their BSc and MSc classes. So mu 0 Ni is now you make it, and we cannot make very long solenoid because these particles travel at very high speed. So what to do? You make it in a toroidal, join the two ends and make it in the plasma here, then it will remain confined in it. So, plasma for fusion, instead of what is happening on sun with the gravitational force, we can have the same with the magnetic confinement here. We can have with magnetic confinement here, and it will require generating and holding temperatures in excess of 150 million degrees centigrade. So how to go about it and what? Okay, before going into the details of it, you may be thinking that there is a alternative solution, nuclear fission, and now we are having many nuclear power reactors. It's good. Yeah, they can to some extent solve our energy problem, but they are dangerous. So dangerous in a sense that if
Excuse me, ma'am.
Hello.
मैम सॉरी फॉर यस मैम मैम सॉरी फॉर इंटरप्शन बट आपकी स्लाइड हम लोग को शो नहीं हो रही है.
Oh, अभी
Yes,
अभी
ma'am.
अभी शो हो रही है?
Yes, ma'am. Yes, ma'am.
अभी let me go to the presentation mode now. Now?
Yes, ma'am.
अभी हो रहा है. So I am changing the slide. Change हो रहा है slide?
No, ma'am. Slide change नहीं हो रही.
नहीं हो रही है तो मुझे इस मोड में ही देना पड़ेगा लगता है. ओके. अभी?
Yes, ma'am. Yes, ma'am.
हाँ. Okay, so we'll proceed with this mode itself. So, nuclear fission and fusion. So, fission is a bit dangerous in a way that it has highly radioactive particles, and energy released in fission is a million times greater than released in chemical reactions. In some ways, it is good, but it is difficult to control. Whereas if you see fusion, now, first of all, probably I forgot to say how fusion can occur. Fusion occurs fission occurs in a heavy material, heavy nuclear material elements, uranium, etc. They become they are not stable, and then they emit the various particles, alpha, beta, gamma, etc. And during fission, when the nuclei breaks, you get a lot of energy. Whereas in fusion, you join lighter elements like hydrogen and its isotopes, and then when the helium atom is formed, there is a mass defect that comes out as energy in fusion reaction. So in fusion, the advantage is that few radioactive particles are produced. High energy is required over electrostatic repulsion. I mean, this you have to provide high initially. And fusion releases 3 to 4 times greater than energy released by fission. So hydrogen isotopes, deuterium and tritium are possibly primary fuels, and deuterium is available in seawater. So comparatively, it is easy to control. Also, less if some accident happens, it's not required that you wait for some hundreds of years for radioactive elements to decay. All of you, I think, remember Chernobyl, and then this Japanese accident that happened. And the place where such accidents in fission nuclear reactor happens, you cannot use those places for a large number of years, sometimes even hundreds of years. So fusion is easy in a way of handling it, even if something happens by accident. And here you all see, you are from, I think, 10th class, 11th class onward, there's reading this equation. And now the fusion reactor is actually a field. I mean, that yes, E equal to delta mc square, that mass difference of about 0.02 AMU, giving 17.6 MeV in a reaction. So let us have a quantification as a how much energy one can get from fusion reaction. So if you see, here is a comparison. If you need this much quantity, say 2 million tons of coal, for producing certain amount of electrical power, then for producing the same amount of power, you need the oil, 1.3 million tons. But how much do you need deuterium, tritium? Just this one small truck. So 30 liters of seawater giving 1 gram of deuterium, energy equivalent to 9,000 liters of पेट्रोल. तो भाई अब आप लोग जो फ्यूचर जनरेशन है, दे वी लुक फॉरवर्ड टू देम, एंड पानी से बिजली बनाने वाला जो फंडा है वो आप लोग को ही पूरा करना है आगे जाके. So so where tritium comes naturally on Earth when cosmic rays interact with the atmosphere. Most tritium is available made via neutron activation of lithium-6. Well, we'll not go into these details. Any reactor, nuclear reactor, uses a moderator, and this moderator, after uh, doing its purpose, is stored, and this water, from this water one can take out tritium. So in India also we have a unit at Madras doing that. So, all the story was about nuclear fusion. It's natural, it's safe, it's environmentally friendly, it's conservation friendly, it's international because it requires a lot of money, and single country at present cannot make a reactor. Later on, once the technology is proven, they will be doing it. We'll come to it in my further slides. So it's unlimited, it is of industrial scale, it's exciting, it's achievable, it's the future. Therefore, you all have to tighten your belts to indeed develop this technology for the mankind. So now, what do we do? Fusion by plasma. So what we have to do here? We have to create a plasma using fusion gases, reach high temperatures, continue adding appropriate fuel, obtain sufficient density. So how it happens? Let me go to the presentation mode. I have some videos to play. I don't know if you all can't see it, let me know. Are you able to see the slides? Hello? Hello?
Yes, ma'am.
Yeah.
Yes, ma'am.
So you are able. Yeah. So what we have to do here in fusion by plasma? We have to confine sun. So create, confine, and control. So this is what you have to do. That is, put a sun in a bottle. Okay. So bottle can be very high, of a very high technology with the superconducting magnets and whatnot. But in a very layman language, if I say that this is what you have to do to confine a sun into a bottle. Bottle में उतार दो sun को और आप future generation के लिए electrical power पाओगे. तो इस तरह, as simple as that, but yes, technologically very challenging. So what we have to do in fusion is we have to bring in two ions, say, of hydrogen together, and they are positively charged, so they will repel. So there will be an energy hill. It has to go through this energy hill to bind itself to produce fusion. So more the number of charged particles, more possibility of tunneling. So we have to have a high temperature, high density, and long confinement time. Now, how do we go about bottle में उतारना है आपको प्लाज्मा को, तो कैसे उतारा जाए? तो इसके लिए आपको पहले एक बॉटल बनाना पड़ेगा. उसको मैग्नेटिक फील्ड कॉइल्स, एज आई सेड, कि सोलोनॉइड है, उसका दोनों पॉइंट्स अगर हम ज्वाइन कर देते हैं तो हमें एक टोरॉइडल शेप मिल जाता है, और टोरिड मिल जाता है, एंड here you can confine the plasma. So confined in a magnetic cage created by combination of plasma current and electromagnetics. Now what is plasma? You all must be feeling, आपको फील नहीं आ रहा होगा ना कि प्लाज्मा होता क्या है, किस तरह आप what's the feel factor here? So as I said, we have to have plasma in a tokamak. We can initiate in many ways. Ohmic heating, where gases in a tokamak is converted to plasma by high current flowing through it, or through radio frequency heating, where the gas in the tokamak, I said that it is a magnetic cage, toroidal uh, field device which can confine the plasma. So here I'm playing a video. If you all can see, just let me know. Are you all able to see? Hello?
No, ma'am.
No,
Huh?
no,
Video
ma'am.
दिख रहा है?
No, ma'am. No, ma'am. Ma'am, we
Last,
can't see the video.
ये प्ले करता हुआ नहीं दिख रहा है? फिर से मैं करती हूँ.
ma'am, only last screen is visible. Fusion by plasma.
Screen is visible, but the video is, you cannot see. I am putting this, the mercury in CFL is converted to plasma by microwave. Here, if I click,
No, ma'am. No, ma'am, it is not visible.
oh, okay, this one, another
No,
one.
ma'am. No, ma'am.
Okay, anyway, this some problem is there, looks like. So CFL, there is a bulb, you can see this bulb lightened up, right? This one. वो भी नहीं दिख रहा है. Oh, okay, never mind. So, plasma, I'll try to explain. So you can see in the YouTubes later on that radio frequency heating, where the gas, supposing you have some mercury in the CFL bulb and you put it in the microwave, so it's converted, that gets converted into the plasma. Even if you put the neon lamps in a microwave environment, they get lighted up. So plasma, what happens is this absorbs, and another example also, I'll try. How to confine this slide you can see?
Ma'am, it is visible, but try to minimize the screen and then conduct the video again.
वीडियो प्ले नहीं हो रहा है. अभी भी नहीं दिख रहा है.
Ma'am, please represent the screen on which the video is going to play and minimize this screen.
Okay. Anyway.
Ma'am,
No, I don't have it separately. I have it included in this. I'm able to see it.
Ma'am,
Now it is visible.
how to confine a fusion plasma? This slide is visible.
How to start, how to confine them. Okay, let's forget about the video. We'll see later how. So, I tried so that you all may have interest, and videos make you more interactive. That's why I had put some videos here. But anyway, due to some technical problem, it's not coming. Plasma in a tokamak can be confined using magnetic fields. Various types of coils are used to confine the plasma as well as position the plasma in the tokamak. So we call them toroidal coils, poloidal coils, etc. And these coils carry current and produce a magnetic field in the toroidal direction. And the charged particles gyrate around the field lines and get confined. So there is a magnetic field line, you all have, I think, must have read that if there is a magnetic field line, the charged particles gyrate around the field lines, and hence simple term में बोलेंगे तो magnetic field lines are like a road. As for the cars or the trucks, the roads are. So same way, the magnetic field lines provide path to the charged particles to move around. Otherwise क्या होगा, गैस डिस्चार्ज जैसे ये पूरा भर जाएगा डब्बा और नथिंग विल, कन्फाइनमेंट नहीं रहेगा उसका. सो टू कन्फाइन इट कि ये चार्ज पार्टिकल इसके अलोंग मूव करता जाए, you will have to have a magnetic field line around it. अभी दिखता है क्या वीडियो? नहीं दिखता.
No, ma'am.
Okay, no, let's not worry about the video then. Okay. So, we'll skip this slide because this is a little bit more technical. And now, as I said, that we have to confine, we want to make a fusion reactor on Earth. Fusion reactor like Sun on Earth. So what should we do? We can confine it through magnetic field lines, the plasma. As gravitational field is playing the role on the Sun, we can do the same on Earth using magnetic field. So in this regard, research started in India long back, but still a long path to go. Aditya, the name itself is, like sun. It's the India's first indigenous tokamak. This only confines the plasma. The fusion it is not a fusion reactor. It is a confined. We had to learn step by step. So how to confine the plasma was learned through this machine. It is still running in IPR here in Ahmedabad, Gandhinagar, Ahmedabad. And here many people learned how to confine the plasma because many phenomena of physics happen when you try to confine. Then there was a small tokamak at SINP Kolkata. They have imported it from Japan, very small one. Then SST1, steady state superconducting tokamak, India's first indigenous superconducting tokamak. Now I'll explain as we go ahead how it is and why what all field of technologies are involved in it. As you are not able to see the video, so we'll go here. World tokamak. How many tokamaks are confined? Like which? Around the world, they have been trying since long to make the sun on Earth, and still a long way to go. As I said, they are still learning how to confine the plasma perfectly. So there are about 200 tokamaks across the world in various countries. So initially, when it started, we went ahead with a very small volume of plasma to be confined. And as the years are passing, we are going forward to more and more volume of these ionized particles, confining them using magnetic field. So right now, with the help of various countries, this machine is getting built, ITER. iter in Greek means to begin. So this reactor is getting built in France. I'll come to it in detail. It's a huge project, very big one. You can see, if you feel that how much a Tesla is, it will have a magnetic field of 5.3 Tesla. I think I have to make much simpler the things, because let me come here. Okay. What is the huge tokamak and what it comprises of? You see, here there is a plasma. So this plasma, ions and electrons are confined. To confine them, you need magnetic field. So this golden colored things are magnetic field. They are all superconducting magnets. And to give these superconducting magnets, they can operate at low temperatures. So they have to be kept cool to liquid helium temperatures. So in order to that, you need a vacuum insulation. And this whole dabba is called cryostat. And can you imagine how much big this cryostat is? It is 30 meter height, 30 meter, I mind my words, meter diameter, and has a volume of about 16,000 meter cube. And you know who has built it? India has built it. And this is already getting installed in France. So the largest vacuum vessel was built in India.
Ma'am, that slide is not visible.
Huh?
Ma'am, that slide जिस बारे में आप बता रही हैं वो slide हमें दिख नहीं रही है slide.
अभी है? अभी
Yes,
है?
ma'am. Yes, ma'am.
ये ईटर लिखा हुआ दिख रहा है? ITER.
Yes, ma'am.
Path to energy from fusion.
Yes,
Slide
ma'am.
का heading है path to energy from fusion. Okay. So this machine is getting built up in, this is an experimental fusion reactor, and this reactor is coming up in France. So India is a partner to this project, and India will be supplying 10 items out of it. One is this huge size cryostat. In एक मॉल है पूरा, आप मॉल में जाते हैं ना, तो एक मॉल के साइज का वेसल है, और इसके ये जो पोर्ट्स दिख रहे हैं आपको, ये इतने बड़े हैं कि एक मारुति कार इसके अंदर से चले जाएगी. तो वेरी बिग मशीन. और ये जो इसके अंदर ये है, इसको हम वैक्यूम वेसल हमारी टर्मिनोलॉजी में बोलते हैं, और इसके अंदर ये पिंक आपको प्लाज्मा दिख रहा है, राइट? और इस अराउंड दिस प्लाज्मा इज कन्फाइंड बाय these superconducting magnets. So fusion research requires then lot of things. So again, another picture of it showing that what is India's contribution to this machine, which is coming up in France. This cryostat, as I said, ये जो vacuum insulation देगा इसको, these are the magnets, the superconducting magnets. Blue colored thing is plasma. So this whole vacuum vessel is built in India at L&T Hazira and transported. Right now it is complete. All the sections of it have gone to France, Marseille, France. You can type on Google and search for this machine, ITER, International Thermonuclear Experimental Reactor. So India is doing many things in this. The supply lines for cryogenic, that is helium and nitrogen, are being supplied by India. power supplies are supplied by India. Some of the power supplies are supplied by India to stop the neutrons that come from here. We use borated steel in this double wall vacuum vessel. Those are supplied by India. So I would say that there are a number of technologies where the world is waiting for you all. If you really venture into it, then the technologies which are awaiting for your brain to show, whatever power it has to really have a challenge in to make the world comfortable with these technologies are. Now I'll just name a few. Okay. What all are things wherein you all can really go ahead is cryogenics. That is how you will supply a lot of helium, liquid nitrogen, how you will make a plant of producing helium, liquid nitrogen, etc. Then, hello. Sorry, अभी मैं बात नहीं कर सकती. So here you have to know all the materials. The neutrons will be bombarding on these materials, changing the form. So many things one has to learn about material development. Many things one has to learn about developing such huge size superconducting magnets in India. The power supplies of various kinds are required. Now, once the plasma is formed, how we will know what it is doing inside? So you need to have a lot of diagnostics depending on the signatures they give, like infrared cameras, scattering through, you put something inside and then scattering you are observing. Then various magnetic probes are there. I mean, you name it and things are here. So it's an engineering marvel, this machine. All fields of engineering are required here, mechanical, civil, you name it and all are here. So the youngsters have a very big job, and such a machine right now, about 9 countries have united to build it in France because it requires huge amount of money. Later on, when this is successful, each country will be required to have their own fusion reactor. So there is a lot of opportunity here for you all to do your best and learn the things and really contribute to the country in this field. So as I said, again and again I'm showing this picture because this is, you can I also suggest that you all go to the YouTube, go to Google and search for this, because this is something very fantastic engineering marvel that will come up in the world. So as I said, India is contributing in 8 fields to this machine which is coming up in France. And okay, so power from fusion reactor, to your generation, I can say that ITER will be by 2035, it will be ready, this machine will be ready. This is experimental fusion reactor. Then there is a plan to go for demo reactor, then fusion power plant. So, lot of things for you all to do. Your generation should tighten your belts to do so. And now I'll come to what I do here. I mean, I was one among you all, sitting and learning what physics, MSc physics, solid state physics, etc., in RDVV University, and how I came up till here, and now what am I doing here, so that I expect more and more scientists and technologists come from our Jabalpur city and do their best to, develop this reactor. So what do I do here and what have I done? I was also a girl like you all are right now, fearing at every stage I mean, as if the world is very brilliant and very intelligent and I am nowhere. No, don't think in that way. Keep on, you fix your aim. If you fix your aim, yes, I have to achieve it, you can do it. So, 35 years down the lane, I was also fearing to go to any IIT. And today I'm in a position that I can give some projects to the IIT students to develop some new technologies. So, girls and boys, gear up. And now I'll just brief you what do I do here. So as I said, this is a very big vacuum vessel, and in this vacuum vessel we have to create vacuum. Now to create the vacuum you need pumps. So just to give you a feel that what order of vacuum is there in this and this cryostat huge size, we are at present at a pressure of 1000 millibar. आप पे मुझ पे सब पे अभी 1000 millibar का pressure है. So as we vacuum, let me say a few lines on vacuum. As you go above the sea level, the pressure becomes less, and and in space when you go, the pressure still goes, and there is no atmosphere there. So the order of vacuum goes from 1000 millibar at sea level to 10 to the power minus 14 millibar in space. And in this vessel, we require a vacuum of the order of 10 to the power minus 9 millibar. So what to do? Here there are so many limitations wherein commercially available solutions cannot be applied. So, and also to make the plasma, you have to fuel something. So, what kind of fuel to inject so that the efficiency of fueling is good? And I am involved in the exhaust and fueling technology development for this project. So here I'm showing you, supposing this side is the fusion machine, then, DT plasma, this is the fusion machine. It requires fueling. Apart, how you will fuel, for that another area is there, storage management, etc. Then you fuel and some unburnt fuel will be there, which has required to be evacuated. So various kinds of pumps are required to evacuate. So I am involved in this part of the technology, fueling the system and vacuum pumping. Hope I am audible. Keep telling me, otherwise I'll keep on saying and to the walls here. Am I audible? Hello.
Yes, ma'am.
Okay. keep saying, वो क्या हिंदी में बोलते हैं ना, हुंकारा भरते रहना, नहीं तो मैं दीवालों से बात करते रहूंगी.
Yes, ma'am. Yes, ma'am.
Okay. अभी ये दिख रहा है ना स्लाइड्स आपको?
Yes, ma'am.
तो अभी हम आगे चलते हैं. मैं आपको बताती हूँ कि मैं भी आपके जैसे एक सिंपल जबलपुर यूनिवर्सिटी के एक स्टूडेंट थी. बहुत डरती थी आईआईटी में एंटर करने से कि सभी लोग मुझसे बहुत होशियार होंगे, मैं कुछ नहीं, इनके सामने मैं कुछ नहीं हूँ, एटसेट्रा एटसेट्रा, जो एक स्मॉल यूनिवर्सिटी के सभी बच्चों में रहता है. बट देन मेरा एक यही था कि नहीं, मुझे आई वांट टू एंटर लाइक in some IIT or a very good scientific organization. So I gave exams after my MSc in various places, Institute of Physics Bhubaneswar, IIT Bombay, then TIFR, many places I got, I cleared written, but I was not able to clear their interviews because coming from a small place, I was not very conversant in English and was very much fearing when I used to see them, all the white-haired scientists sitting there asking questions. So at times I used to get nervous. But then after a few failures, finally when I came here at Institute for Plasma Research to give the interview, I got selected here. There is a big role of Mr. Mehra from St. Gabriel's, who was my mathematics teacher. He used to, keep encouraging me that yes, you can do it. Yes, you can do it. You know what? My father was not in a good financial condition to support my education. So at that time, the key for holiday Resnick was not available. So he used to tell me that every month he'll give me 250 rupees and I have to solve the physics, the assignments that are given back at the holiday Resnick book. So if I can solve them a few chapters every month, if I solve, say, 2 chapters, he'll give me 250 rupees. And that was, at that time, sufficient for me to buy the books. So I accepted it. But that was a very constructive way from his side to support me. And with that, my concepts improved. And I probably, because of him, I am thankful to him, although he is no more. He was my maths teacher at St. Gabriel's School. So he gave that, the hard way to make me complete my education. So I solved a few chapters of Holiday Resnick for him, and it helped me to improve the concepts. And I clicked the interview which was taken at Institute for Plasma Research. So I'm saying that you all also can do it. And we, being from Jabalpur, I know that the children there are very charismatic. They can do, but at times they find the easier path to go, and the brilliance which they have gets lost in some low scope work. And the country suffers, the country suffers. It's kind of brain drain. Children who can really excel and they do something else wherein they don't get the opportunity to go ahead. So it's not only that there occurs an external brain drain when the children go to foreign countries, etc., but internally also I feel that a lot of students lose their path, which probably they could do much better in respect of developing and making the country go ahead in the field of technology. तो ये तो चिंता ही नहीं करना है कि हम जबलपुर से हैं, छोटे स्कूल से हैं, या हम स्मॉल कॉलेज से हैं जिसमें ज्यादा फैसिलिटी नहीं है, एटसेट्रा. अभी तो काफी इम्प्रूवमेंट हो गया. यू हैव, एज आई सेड, पूरे दुनिया आपका एक क्लिक ऑफ अ बटन पे है, आपके मोबाइल पे. तो एक ठानने का देर है, बस एक ठान लीजिए कि मुझे ये करना है, तो आप कर सकेंगे. तो मैं यहाँ पे क्या करती हूँ, आई जस्ट टेल यू. मैं फ्यूलिंग करती हूँ और वैक्यूम पंपिंग करती हूँ. इसके लिए आई हैव डेवलप्ड टेक्नोलॉजीज. ये इतना मैं डीप में तो नहीं जाती हूँ, लेकिन ये बताऊंगी कि what I do here is only done at Oak Ridge National Lab in USA. And after that, the injector which we have developed in our lab here is the only injector after Oak Ridge National Lab, and India has that technology, and it is also installed on our SST-1 machine to fuel pellets. Now, what is it? Just to give a glimpse, it is a hydrogen pellet frozen at about 10 Kelvin, and then it is frozen using some cold zone. Then we use high pressure helium propellant to push it so that it acquires some acceleration. It's in short, if I say in a very simple way, it is a small missile. A missile which is propelled by helium propellant, because we need to use lighter gas. But if we use hydrogen, then hydrogen has all hazards of catching fire, etc. So we use helium. We push this pellet, and can you imagine to what all velocities? To about 1.5 kilometers a second, to such high velocities. And then to supply continue this machine is coming up in my lab. It is called extruder kind of pellet injector. Here we freeze one by one. Here we can supply continuously by freezing the hydrogen and then extruding it using a motor. बहुत सिंपल तरीके से बोलूँ तो वो सेव बनाने की मशीन होती है किचन में, but with all cryogenics etc. that you press it and you get the गाठिया वगैरह नहीं बनाते हैं. So, but this is you have so many technological things here. You have to have a liquid pre-cooler cooling the normal gas to 80K. Then you have to have a liquefier liquefying the gas to the hydrogen. Then a solidifier wherein you put the hydrogen as a solid and then we press it, extruding it as a filament, then cutting it at a very high frequency, propelling it through a helium propellant and pushing it into the fusion machine. So a lot of things, and to let you know, just have a feel. See, these are the pellets taken through a very high speed camera. And this is the injector my group has developed and is put on the machine SST-1. This is, we are coming up with the new injectors, other activities of, still we are building 4 or 5 injectors of different categories. So the speed of these pellets is in the range of 800 to 1 kilometer per second inside the plasma. So this is one. So you see a girl from RDVV from Home Science College who was teaching in the Home Science College, roaming in the corridors of Home Science College Physics Department. was given the task of leading the project uh, of developing pellet injector system for fueling tokamak. And if Ranjana Gangradey can do, all these girls and boys who are attending my lectures, they can also do. So after Oak Ridge National Lab, India has this system. It's a technological breakthrough which we had. I mean, I'm very happy whenever I see this system that yes, after we don't have to beg around anybody in the world to give us this system and the technology. India has it. India can provide to others. Coming to the exhaust, as I said, I have another portfolio of vacuum pumping, evacuating this because plasma you cannot form in atmosphere. You have to do the vacuum pumping for it. I mean, you have to create a vacuum inside this to from 1000 millibar atmospheric pressure to 10 to the power minus 9 millibar. So, how to do about now? If I again show you, just to have a feel, I have to pump out this kind of machine. The volume that I have to pump is about in the range of 1000 meter cube. Similarly, this part has to be pumped out. So for all this, you need vacuum pumps to suck the air from this and remove. Now, the challenge here is you cannot use simply commercially available pumps. Why? Because there is a lot of magnetic field around this machine, and if you use any mechanical pumps, then what happens is these pumps have moving parts, and high magnetic field will have the induced current set up in the moving parts and will block these pumps. So you cannot have anything mechanically moving inside near to this machine. And also the opposite requirement is that you have to keep the pump very near to the machine. Reason being, you will lose a lot of pumping speed if you keep it far due to transmission loss problems. So the available pumps are not having much higher pumping. The commercially available in market are not having large pumping speeds. They have moving parts, etc. So to overcome that, we went ahead with developing a pump by ourselves in the country. These are all imported right now from foreign countries. So my group, the group which I head, all my colleagues, we went ahead, had a thought that we'll develop it within the country. So this, again, I am repeating so that you can imagine. See, this is the man here and the machine size is so large. So this has to be pumped, cryostat has to be pumped. There are other things, neutral beam, etc. They have
Ma'am,
to be...
that slide is not visible.
Okay.
Ma'am, that slide is not visible.
अभी है? अभी है?
No, ma'am.
No, ma'am.
No, ma'am.
Okay, again.
Ma'am, nuclear fission and cryopump slide is visible.
Visible? Is it in the presentation mode or PowerPoint mode?
Ma'am, it is PowerPoint mode.
PowerPoint. Okay. Nuclear fusion. Which slide is it?
Ma'am,
Nuclear fusion, exhaust and fueling technology.
Pallet fueling.
Okay. So this is
Ma'am, again,
visible.
exhaust and fuel technology.
Okay. 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 So going back, I'll just this, as I said, that we have to pump out. A minute. Just a minute. Okay. So this volume has to be pumped out, and we in India, our institute took a project to develop the cryopumps. Here we were, right? Exhaust and vacuum pump compatibility. Is
Yes, ma'am.
lighting there?
Yes, ma'am.
Okay. So, to pump out such a vessel, there was no commercial solution available. And we went ahead with the development of a pump for this. So, okay, I'll try to simplify the things. Um, see, if you cool something, what will happen? Like if you put an air conditioner on and at 16 degrees, say, and the window panes become very cold. So in rainy season, what you see the water droplets on the other side, right? So that is, there occurs a condensation of water vapor on those fans. Now, similarly, when we cool a surface, the gases can condense on it. So when these gases condense on it, they can create vacuum inside a closed chamber. So what phenomena of physics governs it is saturated vapor pressure of these gases. So if you cool these gases, here is a chart showing that if you cool these gases to low temperature, if you cool a surface to a low temperature, then you can get a vacuum inside. So what we went ahead with a very indigenous solution. We not only cooled the surface using liquid nitrogen and liquid helium, but we, if I have 1 square meter of surface, say, and I cool it, then on 1 square meter of surface, I can deposit the gas molecules. But how, keeping the cold surface as 1 meter square, how can I increase the surface area where these gas can get absorbed? So the solution which we went ahead was using coconut shell charcoal. All of us eat a lot of coconut, especially in our South India. Every meal has a coconut in it. So they can eat the coconut as much they want. We want the shell of the coconut. So we developed a porous material from the shell of this coconut. And this 1 spoon of activated charcoal is so porous that it gives an area of about 1300 meters square in 1 gram. So inside it, the picture is in one piece. This is 1 piece of charcoal. You can see how many holes are there in this. So the gases can go and get absorbed on this. So 1 spoon of this coconut shell charcoal can give, for the gases, it can give an area of a soccer field. So if you put this charcoal on 1 meter square of a surface, you can get an area which is 1300 meters square, right? 1 meter square for 1 gram. 1 gram of it can give 1300 meters square. So you can get a huge area, and Using this, we went ahead with developing a cryopump. So I'll come back to the roadmap later. So technologies involved, well, many technologies are involved. We have developed all these technologies in the country, all Indian made. Total पूरा भारतीय क्रायो पंप बना दिया हमने. So right from sorbent, adhesive, sorbent characterization, मतलब अगर आप कुछ चीज सिलेक्ट करते हैं तो उसको क्रायोजेनिक कंपैटिबल होना, मतलब जैसे आप कुकर का रिंग है उसको लिक्विड नाइट्रोजन में डाल देंगे तो टूट जाएगा, तो आप वो रिंग को लिक्विड नाइट्रोजन के फील्ड में यूज नहीं कर सकते. इसलिए हर मटेरियल जो है आप सिलेक्ट करते हैं दैट हैज टू अंडरगो material characterization with respect to compatibility with vacuum and also cryogenics. So ये सॉर्बेंट नहीं था इंडिया में, मतलब था पर हमारे हिसाब से नहीं था. So we went ahead with developing this activated coconut shell charcoal giving large surface area. अभी ये चारकोल को एक स्टील के पैनल पे चिपकाएं कैसे? सो ये एडहेसिव्स यानी 4 केल्विन टू 450 केल्विन तक ऐसा एडहेसिव जो कि चारकोल को स्टील पे चिपकाए, that was not available. So we went ahead with developing that adhesive. Then sorbent में माइक्रो, मतलब pore size should be less than 2 nanometer. So we have to characterize these sorbents. Then physics study of a geometry wherein how many particles are launched and how many particles are able to reach a surface. Then all the thermal and structural contractions and structural design for it, analysis for it. So and then developing a pump, doing the pumping study, valve development, etc. So many technologies were involved, which we one by one we developed. Now we have developed the first liquid helium cryopump, liquid helium based cryopump, and this can pump helium and hydrogen. Then we went ahead with the single panel larger scale, that is 14. This was giving 2000 liters per. This is our first pump, giving us pumping speed of 2000 liters per second. Then we went ahead with 14,000 liters per second. Then we went ahead with 150,000 liters per second pumping speed for hydrogen. So the technology got developed in our institute. And then ISRO also requires this cryopumps for evacuating cryovac chambers. Satellite जब बनता है तो satellite can ऊपर space में vacuum है. So every satellite has to undergo a test of vacuum compatibility. And hence each component of the satellite is tested in a vacuum chamber for its vacuum performance. Also, the complete satellite, when it is assembled, is tested for the vacuum performance and thermal cycling. And for this, there are huge size. I mean, double the size of what I have. If I can relate to the physics department at Home Science College, if I remember, I mean, if the lab is same, then the height, that electronics lab was there, I still remember that. And the height, if you double that height, I mean, such huge vacuum vessels are there. These are required to be pumped out. And for that, they need these cryo pumps. So we had signed an MOU with the ISRO SAC and for developing cryo pumps for ISRO. So you can see myself, my director, signing the MOU with the ISRO director here. So we went ahead with India's first cryogenic vacuum pump, developing it. All the technologies were developed in India. So it's a made in India cryo pump. And see here, my group people are coating the cryo panels, the fabricated cryo panels, testing the solvent for its characterization. Here is the pump getting tested. So, cryo pump for SAC ISRO we had developed, and now this pump we call it Agastya, the gas trapping yantra. Why? Because this has a 400 mm opening, and this pump can provide pumping speed of 5,000 liters per second for air, for water about 15,000 liters per second. So you can, if there is a requirement for still bigger, one can go ahead with increasing the diameter of it. We have named it Agastya, a gas trapping yantra. Why? Because there is a story that Rishi Agastya, there used to be fight, between the demons and the devatas and the rakshasas. So once it happened that all the rakshas people, they went and they made themselves to hide in the ocean, and devatas were not able to find it out. So they went to Agastya Muni, who was in fact a real scientist. You can read about him. There are beautiful stories about him. So he went, they prayed to Agastya, and he drank the water of all the oceans. So this pump, Agastya, for its size, has enormous black hole pumping speed for water vapor. That is why we gave it the name Agastya. So it is our Agastya 400, we call, because it has opening of 400, and it is installed in ISRO now. This is the team IPR and team ISRO involved in we have developed it, and we were testing for the cryopump for that. And here you see that this is the IPR supplied cryopump on one of the SAC ISRO cryovac chambers getting tested. So it's getting tested. So I end my talk here. Thank you, all of you, for listening to me. And this is what all I have to say regarding what we went ahead with the developments, etc. Any questions are welcome.
Thank you so much, ma'am. Yes, ma'am. We have collected some questions to you from our class.
Okay. How to go about answering?
Ma'am, first I want to ask, what will be the new possible research areas in plasma physics in future?
Okay. Many areas are there. Like one I said, wherein I was involved, fusion reactor development. In this itself, there is a research area of going ahead with developing superconducting magnets. And superconducting magnets, there is it itself is a very vast area with various kinds of materials. Right now we are using niobium, titanium, or niobium tin kind of things, NB3SN, NB3Ti, etc. And all these each material has some limitations of going ahead with the power it can handle. So as we the requirement for better and better superconductors is on its way. I mean, the requirement is growing and growing. Apart from that, there is a high temperature superconductor material research. We cannot, keep ourselves limited to the superconductors working at liquid helium temperatures. We want that we get high temperature superconductors and with which we can make the coils, so that the dependency on cryogenics is reduced, because cryogenics is a cumbersome thing, bringing in so much of complications with respect to transferring the cryogen, cooling, thermal engineering, perfect leak tightness, etc. So this is one field. Then there is a field of going ahead with developing various kinds of power supplies. Challenging power supplies are there. Then there is my field of ultra high vacuum and fueling methods. Then there is plasma for industrial application. Like plasma is good in various. We have another institute which we call it as FCIPT, wherein we use plasma for industrial application, for biomedical applications, making plasma torches, etc., for cleaning of tooth and dentist and skin artificial skin development. I mean, there are so many things. Industrial application of plasma are a number. Like even in the agriculture, one can use plasma to treat seeds, etc., so that good crop is available. I mean, variety of fields are there. Hello.
Yes, ma'am. Thank you, ma'am. Next question. Next question, please.
Good afternoon, ma'am.
Yeah, good afternoon.
Yes, ma'am. First of all, ma'am, thank you so much for giving us your precious time.
It is my pleasure. You all are, I was in your place 35 years ago, no? So it's my duty towards my university.
Yes, ma'am. Ma'am, my question is, ma'am, my name is Ayushi Patel, and I am pursuing MSc in Physics. And ma'am, my question is, ma'am, what advice would you have for us to set a career in your field?
Your voice is not clear. It's breaking.
Ma'am, my question is, what advice would you have for us to set a career in your field?
Okay. In this field, it's not that you can get involved in the fusion program of the country just by joining the institute. Although you are all most welcome. There are various advertisements that keep coming on our website, ipr.res.in. But you can contribute to the field of fusion and plasma technologies even by joining various other organizations like the industries, because we have finally to give the product to be developed to some industry. So depending on your interest, where you want to really go in, through various methods, I mean, you can get involved. There is a requirement, as I said, of physics field in lasers, in semiconductors, in going through the data coming from scattering, I mean, that the various diagnostics that are there on the fusion machine, they are all physics based. So um, one can, venture out. You can have a look at various YouTube. Most of the things are available on YouTube, so you can go through it and pick up where you want to really go, which field you want to select for.
Okay, ma'am. Thank you, ma'am.
Ma'am, I want to
Thank you
ask,
so much.
ma'am,
Yeah,
there is one question for
yeah.
ma'am. When we talk about nuclear reactors, there is much more harmful radiations produces. So how will we reduce them in a good manner?
Okay. In fusion, that's not happening. Whereas in nuclear fission, those reactions that are taking place and radiations that evolve, I mean, you need to have a lot of thick lead walls around the machine to stop these radiations going far. And this is the field wherein BRC is working at Bhabha Atomic Research, Trombay. In fusion, as I said, tritium is involved. If we go till now, we are learning right now only to how to confine the plasma. Hydrogen, no radiations are there. Deuterium also, low speed neutrons are there. But when we go for tritium, yes, tritium is radioactive, but it is harmless. Even its half-life is about 12 years. So even if some components say get the tritium absorbed in them, we just place them aside for 12 years
Ma'am,
and can reuse it.
excuse me, ma'am. Ma'am, we have a possibility for thorium now.
Thorium. Yes, well, as I said, that's not my field. Fission is not my field. My field is fusion. But our country is rich in thorium, and this thorium has to be enriched. Kerala, a lot of thorium is available, and government is trying with the going ahead with the program of using this thorium for nuclear reactors. But these are all fission reactors. The government has a plan of putting up 47 fission reactors at present all over the country. Uh, and in that, they'll be using the thorium. I mean, some of them will be based on thorium and enriching of thorium. The plants have to be set up for that. So, yeah, I mean, one can go ahead with that as well. But I'm not working in the fission field. I'm working in the fusion, nuclear fusion.
Ma'am,
Yes.
Thank you, ma'am. I would like to thank our distinguished speaker, Dr. Ranjana Gangradey, ma'am, for making an excellent presentation and making this webinar very meaningful and interesting and sharing very efficacious and valuable information about how our energy requirements will increase in the future, and nuclear fusion can be a major source for supplying large amount of energy, and it is an everlasting environment friendly and international energy source. Really, for us, this information by our speaker, ma'am, will be very helpful for our future study career. This field of technology is very emerging, engrossing, and bearing endless research and career opportunities in it. It's my privilege to have been asked to propose a vote of thanks to this informative and useful webinar. I, Shivangi Agrawal, MSc final year, on behalf of Department of Physics, is here to extend a very hearty vote of thanks to the guest speaker, Dr. Ranjana Gangradey, ma'am, who spared time from her busy schedule. Thank you, ma'am, for your thought-provoking and interesting address. I also thank to Dr. S.G. Johri, ma'am, Dr. Srivastava, ma'am, Dr. Paliwal, ma'am, Dr. Verma, sir, Dr. N.L. Patel, sir, and all our respected teachers for supporting such exemplary session. Once again, thank you very much, ma'am. Thank you very much to all who assembled here. Thank you so much, ma'am.
I also thank you all for listening to me patiently, and also my vision is that yes, more people from the young generation should come up, look at developing the technologies within the country, and I have when I can come from a small place and do it, you all also can do it, because you all have more access in the technology right now, from compared to me when I was in 1985, 88. There was no mobile, no internet, nothing. Only through reading through the books we had to know the things, and so and it is my duty that to the students of my university, emerging, buds. They come up in life, they do something good for the country, and it was my pleasure to give the talk to you all. And I hope that I actually wished that I could come in person and give, so that our session could be more interactive. But due to this COVID situations, etc., I thought that my country requires my services more, so better not to risk by traveling. So I wish you all good luck, and I hope that you, knowing that there is there is a field where you can contribute, you all will try for it and do your best in the field. Country requires technological developments, so I wish that all of you really come up and pursue their careers and go ahead with it. So thank you. Thanks to all for attending the presentation. And I'll definitely, if I come there, I'll give a live talk regarding whatever development we have done. So thank you all. Thank you, Dr. Johri. Thank you for giving me this opportunity.
Thank you so much,
ma'am.
Thank you all.